Hello, am I audible and is my screen visible?
Yes, sir.
Okay, thank you. So, good evening, everyone. Welcome to this NPTEL live session for the course Introduction to Machine Learning. My name is Owen Maiti. I'm a PhD scholar in the Department of Computer Science and Engineering at IIT Kharagpur. So, this is my third live session. We will discuss some questions on the topics covered in week 3. And if you have any questions or queries regarding these week 3 topics, you can ask me during this session. And in week 3, mainly logistic regression and linear discriminant analysis, these two things were taught. So we will discuss some practice problems on mainly on these two topics. Okay, so we will start solving some practice problems first, and after that, if you have any other questions or queries, you can ask me. This is the first question. Which of the following is false about a logistic regression based classifier? So you have to find out the false options. The logistic function is nonlinear in the weights. The logistic function is linear in the weights. The decision boundary is nonlinear in the weights. The decision boundary is linear in the weights. So multiple options may be correct in this question, and you can write your answers in the chat. Devashish Paramanik says B and C. Okay. Shweta says A and D. Anyone else? Anantapalli Nagalaxman Kumar says A and C. Okay. Shoham is asking, I couldn't complete the lectures and assignments of previous weeks of the course, so can I complete them now or should I start from the current week? And the assignment deadlines are already over for the first 2 weeks assignments, so I don't think you'll be able to submit those assignments anymore. In that case, you have to start from this week. If it is open for you, then you can start with the first week, but I think it's already closed for the first 2 weeks assignments. Ajit Boral says option C. So multiple options are correct in this question. So the first option says that the logistic function is non-linear in the weights. So logistic function is given by 1 divided by 1 plus e to the power minus theta transpose x. So this theta are the weights. So this logistic function is certainly not linear in the weights. So and the logistic function is used so that it can bring non-linearity in the logistic regression classifier. So the first option, that logistic regression is non-linear, is actually true. So this is true. So the logistic regression is linear in the way. Second option is false. And then third option says that the decision boundary is non-linear in the weights. So in logistic regression, the decision boundary is linear. So if these are the two sets of points, so the decision boundary goes like this, and it is given by this theta transpose x equals 0. Once we find out these theta values, parameters, the decision boundary is given by theta transpose x equals to 0. So this is the straight line that defines the decision boundary, and theta transpose x equals 0. So this is the decision boundary is certainly linear in the weights theta. And also from the overall figure, we can see that the decision boundary has to be a linear decision boundary in case of logistic regression. So option C is not correct, and the last option says that the decision boundary is linear in the weights is correct. So you have to find out the false options. So B and C are the false options here. So is there any doubt in this question? Sweta is asking explanation for option A. Option A says that the logistic function is non-linear in the weight. So logistic function is given by this 1 divided by 1 plus e to the power minus theta transpose x. So this is certainly not linear, we can see. So this is exponential, and then we are again inverting it. So this logistic function is not linear in the weights. So first option is correct. So but you have to find out the false option. So A cannot be the false option. Yeah, you have to find out the false options here. A and D, these two options are correct, and B and C are false. So you have to find out the false options. B and C are the answers for this question. Now moving on to question 2. So this is on linear discriminant analysis, or LDA. Consider the case where two classes follow Gaussian distribution which are centered at 3,9 and minus 3,3, and have identity covariance matrix. Which of the following is the separating decision boundary using LDA, assuming the priors to be equal? So two classes distributed by Gaussian distribution. The centers are 3 comma 9 and minus 3 comma 3 for the two different classes, and they have equal covariance matrices, and prior probabilities are also equal. So you have to find out the decision boundary. So if I simply plot this for better visualization, if this is the first point 3 comma 9 and this is the second centroid minus 3 comma 3, so these are the two centroids of the two different classes. Now you have to find out the decision boundary. There will be a straight line obviously in case of LDA. So what will be the decision boundary? Has anyone found out the answer? Ajit Baral says option C, which is x plus y equals to 6. Haricharan V says option C. Okay. So option C is the correct answer. So two centroids are given for two different classes, and if in case of LDA, if the Gaussian distribution representing two different classes have identity covariance matrices and the prior probabilities are also equal, in that case the decision the separating decision boundary is the perpendicular bisector of the straight line joining the two centroids. So here this red line represents the perpendicular bisector of the line segment joining the two centroids 3,9 and minus 3,3.
Sir,
Yes.
sir, question number 1 is not shown since the network was not there that time.
I think most of the others were able to see. I think you can go back. I mean, these video lectures will be uploaded, and you will get all the these PPTs also, so you can check these out later.
Okay, sir.
So this red straight line represent the perpendicular bisector of the line segment joining the two centroids 3,9 and minus 3,3, and that is the separating decision boundary in case of LDA. So we just have to find out the equation for this perpendicular bisector. So if we consider the equation to be y equals mx plus c, we have to find out the values for m and c from the given information. So first information we know is that this straight line y equals mx plus c goes through this, there is a perpendicular bisector of this line segment joining the two centroids, so it must go through this midpoint of this line segment joining the two centroids. So the midpoint, this midpoint can be computed as so it should be minus 3 plus 3 by 2 comma 3 plus 9 by 2, so that is 0,6. So 0,6 is the midpoint, and this decision boundary goes through that point, so we can simply put this value 0,6 to this straight line, so it would give us 6 equals 0 plus c, so c equals to 6. So c equals to 6. Now we have to find out the value for m, and we know that this decision boundary is perpendicular to the line segment joining the 2 points. So this is perpendicular to the line segment joining these 2 points. So if two straight lines are perpendicular to each other, the product of their slopes m1 equals to m2 equals minus 1. So slope of this line segment joining the centroids, we can find out the value for this value of the slope for this line segment joining the two centroids m dash is 9 minus 3 divided by 3 minus 3, which is, I think it's 1. So m dash is the slope of the line segment joining the two centroids. So m would be minus 1 divided by m dash, so that is minus 1. So slope is minus 1 and c is 6. So equation becomes y equals minus x plus 6. So that gives x plus y equals to 6. So this is how you can find out the equation of the separating decision boundary in case of LDA if the two centroids are given. Does anyone have any questions or doubts in this problem?
So how will we know that it will be the perpendicular bisector from
It is
just
always
the
always the case. I mean, in case of LDA, the separating straight line is such that it will be perpendicular bisector of the two Gaussian distributions. I mean, the centers of the two Gaussian distributions. If the Gaussian distributions have identity covariance matrices and the prior probabilities are also equal, in that case, it always holds.
But this was not mentioned in the lecture. So any more things like this, how we will know from where we will know that there are conditions like this?
Mm, if you go through the process of LDA properly, then I think it can be inferred that if the Gaussian distributions of identity covariance matrices and prior probabilities are equal, then the straight line would be like that. The decision boundary would be like that. I'm not sure whether it is mentioned in the lecture or not, but these sort of things, I mean, you can infer from the topics covered in the lectures.
Okay.
Sir, is there, so here there are two data points, 39 and minus 33.
Yes.
Is it possible in case of 3 or more data points are given?
No, data here, these are not exactly data points, they are the centers of the uh, different Gaussian distributions for different classes. Two classes here are there in this question, so two
Yes.
centroids are there. So yeah, it is possible that there will be multiple classes if there are 3 or 4 classes in the specific question. In that case, it will not be one straight line, certainly. If there are 3
Okay.
classes, the decision boundary would be very different, something like that, separating 3 different classes. So it will not be one straight line.
Okay.
Will the same condition hold true if the covariance matrix is a diagonal matrix and not
Yes,
exactly
yeah.
the
If the classes are almost identical in shape, the Gaussian distributions identical in shape, in that case, each straight line would be perpendicular bisector of the line segment joining them.
okay, any two Gaussian distributions.
Yes,
It need
yes.
not have the same parameters or anything.
Yes. I
So
mean, the
how
Gaussian distributions must be same for both the classes. Their same means their covariance matrices must be same. Otherwise, this straight line would shift towards towards this or this. The straight line would shift. The two Gaussian distributions have equal identity covariance matrices. That's why the the decision boundary goes through the middle. Otherwise, it would shift towards left or right. And also the priors are also equal, so that is also one of the points here.
That where does it come in the plot, or how do we know about the priors from this diagram?
From the diagram you cannot know. Prior basically means how many what fraction of points belong to a certain class. So if both the classes are 50% points, in that case the priors are equal. And if some class is skewed, I mean some class contains 90% of points, other class contains 10%, then the decision boundary would change accordingly, so that would be different. but here priors are same, so the straight line, the decision boundary would go through the middle.
If the priors are not equal, will it still be a straight line, the decision
Yes,
boundary?
it will always be a straight line because this is linear discriminant analysis. So linear is in its name. So the discriminant or the decision boundary is certainly linear always, but the if the priors are not equal, it would shift towards one of the Gaussian distributions based on the probability values calculated.
Sir,
Whatever they have given is the mean of the mean of the distribution, no? The 3, 9, and
Yes,
minus 3,
yes,
3.
yes. They are the
Okay.
means.
sir, the priors to be equal means that the priors lies on the decision boundary, sir.
No, prior. I mean, these pi k values mentioned in the lectures. If you go through those, this is the prior. Pi k is the prior probability for the kth class or class k. It basically means how what fraction of points belong to class k.
Yes, sir. And M1 into M2 is equal to -1 is always this case.
Yeah, it is simple. I mean, 2D geometry, the coordinate geometry. M1 into M2 is -1 if the two straight lines are perpendicular to each other. So this doesn't have anything to do with LDA. This is from 2D geometry.
The perpendicularity condition, why is it coming? All LDA, always it will be perpendicular, the decision boundary, to the means that, to the line joining the means. Huh?
Yeah, it will always be perpendicular, but not always if the covariance matrices are equal. Identity covariance matrices. The decision boundary would be perpendicular to the line segment joining the two centroids, but not always the perpendicular bisector.
Okay.
Now question 3. Logic transformation for probability of x equals 1 for the given data s equals this. So these are different x values 0, 1, 1, 0. So to find out the probability of x1 and then logic transformation for this. Shweta Lakshmi says option B, which is 4/3. Muthu Kumar and Iyer says option C, which is 4/7. Anaga Pankaj Chogaonkar says option B, 4/3. Devashish Paramanik says option B. So correct answer is option B, 4/3. So to compute, first you have to compute the probability of x from this dataset. This is a small dataset S, and this variable x takes these different values 0, 1, 1, 0. So this probability of x equals 1. Please mute yourself. Someone is unmuted. So probability of x equals 1 you have to compute first. So probability of x equals 1, how many times this 1 is occurring in this dataset? So 1, 2, 3, 4 times out of 7, so it will be 4/7. and logit is for this probability is computed simply as this probability of x equals 1 divided by 1 minus probability of x equals 1. So this is 4 by 7 and divided by this is 3 by 7, which is 4 by 3. So this is how you can calculate this logit transformation for this probability value.
Actually, why this log? What is the importance of this logic function?
Logit basically gives you the odds for 1 compared to the other class values 0. This is the probability of 1 and the denominator is the probability of 0.
But only for 2 class it will be useful, no?
Yeah, only to compare two classes, yes. I mean, in LDA,
If there are any classes, we
in
cannot
the
use
LDA,
this.
this log odd was in the LDA lectures, log odd was taught that compared to class 1, what is the odd for class 0 or class 2. So comparing two classes, you can say which class is more likely to result.
What is the difference between that log odd and this logit?
You just take log of this probability of x equals 1 divided by 1 minus probability of x equals 1. Sometimes the log helps you reduce the complexity of the expression by bringing the exponents down.
And when there are multiple classes also, will this be used or only for 2 class problems it will be used?
You can compare at a time only two classes, because in numerator there would be 1, in denominator there would be 1. If you compare multiple classes, then you can form these odds multiple times. If you have 3 classes, you can form 3 such odds, and then based on that you can compute which one is most likely, which
So
class
the
is
one
most
that is having the highest value, that will be the class. Like
yes,
that it will be
yes,
assigned.
yes,
And similarly for logit also.
yes.
Okay.
Now question 4. The output of binary class logistic regression lies in the range minus infinity to infinity, minus 1 comma 1, 0 comma 1, minus infinity to 0. Muthukumaran IS is option C, Devasis is option C, Shweta Lakshmi is option B, Ajit Paral says option A, Kalpana says option C. Anagha Pankaj says option C. Anyone else? Muhammad Ihsan says option C. Okay. Girish Rathore says 0 and 1. So the correct answer is option C, 0 and 1. So in case of logistic regression, the output layer contains, first you compute the theta transpose x for any input x, and then you have to apply this logistic function or the sigmoid function. So this sigmoid function is defined as 1 divided by 1 plus e to the power minus theta transpose x. So this is the actual output of the logistic regression for any input x. This basically tells you the probability of y equals to 1. It returns a probability. So if you plot this sigmoid function, you will get, so this is 1, so this is from minus infinity to infinity it ranges. So this is the x values, and the sigmoid the output of the sigmoid ranges from this 0 to 1. It does not go above 1, and at minus infinity its value is 0. So it ranges from 0 to 1, and in this for x equals to 0 the value is half here. So the output ranges from 0 to 1 in case of logistic regression.
Sir, is it not always monotonic, always increasing?
Yeah, the sigmoid function is always increasing. It looks like this. So it is always increasing, but increasing very slowly, and it as it approaches infinity, I mean for higher values of the input, the it almost approaches 1 and almost doesn't change.
So why we cannot say that minus infinity? Why the answer cannot be A?
No, the value does not range from minus infinity to infinity. Value is the y-axis here. Sorry, this
Okay.
value is the y-axis. The input to this function can be from minus infinity to infinity.
Okay, got it.
Yeah, output is at max 1.
Yes.
Question 5. Logistic regression is robust to outliers. Why? There are 4 options. The squashing of output values between 0, 1 dampens the effect of the outliers. Linear models are robust to outliers. The parameters in logistic regression tend to take small values due to the nature of the problem setting, and hence outliers get translated to the same range as the samples. And option D is the given statement is false. So you have to find out why logistic regression is robust to outliers. Muthukumar and Ayers is option C. Ajit Baral says option C. Sanvi says option C. Anagha Pankaj says not sure A or C. Okay. The correct answer is option A, that the squashing of output values between 0, 1 dampens the effect of the outliers. So in logistic regression, the output, as we discussed in a previous question, that 1 divided by e to the power minus theta transpose x. So whatever is the value of the theta transpose x, this logistic function or the sigmoid function brings it down to the range 0 comma 1. So this theta transpose x value may be very high because of the weight values theta or even for the output, but this transformation or the sigmoid function brings it down to the range 0 comma 1 always. So in case of outliers, this even for outliers or noise points, the value might be very off from the original value, but those values are also brought down between the range 0 comma 1, so they don't have much effect in the training of the logistic regression.
So, sir, so the probability will always between 0 and 1. So, since the probability is always between 0 and 1, the weight will be basically limiting, basically the weight will be limited.
Now, these weight values theta can have any value. That's why we are applying this sigmoid function at the in the output layer of the logistic regression. Theta values can take
Yes, yes,
any
that's
value.
correct.
So, but this transformation 1 divided by 1 plus e to the power minus theta transpose x, this will always result in a probability value between 0 to 1.
0, 0, 1, yes.
Yes. So some of you have written option C, but that the parameters in logistic regression tend to take small values due to the nature of the problem setting, but which is not correct. That this parameter or the theta values can range from minus infinity to infinity, anything, but this logistic function would bring it down between the range 0 to 1. So these parameters taking small values is not correct. If we apply different regularization techniques, then these parameters would take small values, like ridge regression or lasso regression that we have learnt in the previous week. If we apply those regularization, then the parameter values would take small values, but in general it can take any value. Now question 6. We have two classes in our dataset with mean 0 and 1 and variance 2 and 3. So this is the mean of the first class, this is the mean of the second class. So let's say m1, m2. This is the variance of the first class, this is the variance of the second class. So now the options are LDA may be able to classify them perfectly, LDA will definitely be able to classify them perfectly, LDA will definitely not be able to classify them perfectly. Option D is none of the above. Anantapalli Naga Lakshman Kumar says option C, that is definitely not be able to classify them perfectly. Okay. And Devashish Paramanik says option C. Ajit Baral says option B. Okay, so if we try to visualize these two different classes, so these are one dimensional because the mean contains only one dimension, 0 and then 1 for the other class. So the data points are one dimensional. So let's say this is 0 and this is 1. So this is the center for the first class, this is the center for the second class, and variance values are given, but we have to work with standard deviation because that gives you the range within which most of the points would lie. So root 2 is the standard deviation for the first class, root 3 is the standard deviation for the second class. So root 2 is almost 1.4 and root 3 is almost 1.7, almost 1.7. So the most of the points should lie within, for the first class, most of the points should lie within, let's say this, it should be so 1.4, which is around here. So most of the points for the first class would lie within this range. This is 1.4, which already covers the centroid for the second class. And for the second class, where the mean is 1 and the centroid, standard deviation is 1.7, so it would be something like this. So both the classes would obviously overlap with each other. So if the classes overlap with each other, LDA is a linear discriminant analysis. It's a linear, it will form a linear decision boundary. It will not be able to classify them perfectly if the classes overlap with each other. So basically you can visualize the two classes using this one dimensional plotting, and then simply you can see that the standard deviation values are so high that it goes past the centroid for the first centroid for the second class also. So the second class centroid for the second class belongs to the within the range for the first class. So the two classes are overlapping. Basically the Gaussian distributions for the two classes are overlapping. So the LDA will not be able to classify them perfectly. So option C is the correct answer. It will definitely not be able to classify them perfectly. So is there any doubt in this question?
Is there any other method with the help of which we can identify this if the points are something different other than?
Yeah, if these variance values are smaller, in that case if the two classes do not overlap with each other, in that case we can say that they LDA may be able to classify them perfectly. But
How about
yes?
how about logistic regression? Whether it can classify?
No, I mean the points are certainly overlapping. So linear decision boundaries cannot classify them. For example, let's say these are points of one class and these are points of another class.
Mm-hmm.
So linear decision boundaries cannot classify them perfectly, but higher order methods might be able to somehow fit these points like this. Somehow would be able to form some complex decision boundaries, and they might be able to classify them. But linear methods will not be, classification methods will not be able to classify them if the classes overlap.
So with the help of this number line kind of thing, we can find whether they are overlapping or not.
Yes.
That is the only method. Okay?
Yes. Basically, you have to check whether the standard deviation is so high that it crosses the centroid of the other class or not. Here it is 1.4, which is much more than the centroid for the other class 1. So the classes are certainly overlapping in that case. Now question 7. With respect to linear discriminant analysis, which of the following is or are true? Consider a two class classification case. There are three options. Multiple options may be correct here. First option says when both covariance matrices are spherical and equal, the decision boundary will be the perpendicular bisector of the line joining the means. Option B says when both the covariance matrices are spherical and equal, the decision boundary will be perpendicular to the line joining the means. Option C says that when both the covariance matrices are spherical, equal, and the priors are also equal, pi 1 equals pi 2, then decision boundary will be perpendicular bisector of the line joining the means. Multiple options may be correct in this question. Anagha says option C, okay, and B. Devashish says option B, C. Muthukumaran says option A and C. Tejasvi says B and C. So most of you have written the correct answer. The correct answers are B and C. So as I have discussed in in one of the previous questions, that if the covariance matrices are spherical and equal for the two classes, then the decision boundary will certainly be perpendicular to the line segment joining the two means. For example, this is one class, this is another class. Sorry. This is another class. This is the line segment joining the two straight lines. The decision boundary would certainly be perpendicular to each other, but whether it will be perpendicular bisector or not, that is whether it goes through the midpoint of the line segment joining the two centers or not, that depends on the prior values. So which is covered in option C, that if the priors are also equal, pi 1 equals pi 2, in that case the decision boundary will be perpendicular bisector. So in that case it would go through the exactly the midpoint. So it will become perpendicular bisector of the line segment joining the two means.
So perpendicular bisector means that it will be divided into equal halves.
Yes, this straight line, the line segment joining the two centroids will be bisected by the two, equally bisected by the two, this decision boundary. Only if the priors are equal, but if priors are not equal, based on the values of the priors, the decision boundary would either shift to left or shift to right. Now question 8. In general, which of the following classification methods is the most resistant to gross outliers? The three options: linear regression, logistic regression, linear discriminant analysis. Anagha says option C. Muthukumaran says option C. Devashish says option B. Kalpana says option C. The correct answer is option B, logistic regression. This also I discussed in a previous question, that logistic regression uses this sigmoid function, which brings down the value between 0 to 1, which enhances its capability of reducing the effect of the outliers or noise points.
But there is a confusion. It is mentioned there at the most resistance to gross outliers. So resistance means
Resistant means it is not affected much by the gross outliers.
okay.
But will this help to classify those outliers also correctly?
Outliers, we don't need to classify the outliers. Outlier points are such that we should be able to ignore them as much as possible. For example, if let's say this is one class and this is another class, but one outlier point of the other class is here present. It actually belongs to this class, but this outlier point is present here. We should be able to, the classifier should be able to pay not much attention to those outlier points.
I got confused.
Okay.
Resistance means
Resistant basically means it does not get affected by the gross outliers, or it has some mechanism to resist those points basically.
okay.
But the other two methods, linear regression and logistic regression,
They are very much affected. The outlier.
yeah, linear regression is highly affected by that, because it uses the mean squared error. For the mean squared error value for the outlier or noise point becomes very high, because it is computing the difference between the actual value and the predicted value and squaring that. So for the noise or outlier points, this loss value for the noise or outlier points becomes so high that they can affect the training process heavily. And also LDA does not have any such mechanism to counter those outlier points or to resist the effects of the outlier points.
Right. Okay.
Question 9. In a binary classification scenario where x is the independent variable and y is the dependent variable, basically x is the input and y is the output. Logistic regression assumes that the conditional distribution y given x follows a, so which distribution does it follow? Bernoulli distribution, binomial distribution, normal distribution, exponential distribution. Devasis Paramanik says option A, Muthukumaran says option A, Sweta Lakshmi says option C. Anantapalli says option A, Sweta says option A. Amitesh Sahai says option C. Lakshmikant Bhurjana says option A. Yash Mehrotra says option B. Because the correct answer is Bernoulli distribution. So because in logistic regression, this for two class classification problem or binary classification problem, this y value can take only two values, 0 or 1. So if a random variable takes only two values, it follows Bernoulli distribution. So it will be Bernoulli distribution. So the dependent variable is binary, so Bernoulli distribution is assumed at the start of the logistic regression. Now question 10. We have seen the methods like ridge and lasso to reduce variance among the coefficients. We can use these methods to do feature selections also. Which one of them is more appropriate? So these are two different regularizer methods that we have studied in the previous week, ridge regularizer and lasso regularizer. So which one is more appropriate for feature selection, ridge or lasso? Anaga says option A, Muthukumaran says option B, Yash Mehrotra says option B. Manish Thakur says option B, Lakshmikant Urjana says option B. So option B is the correct answer. Lasso regularizer. So ridge regularizer can reduce the values of the coefficients or the parameters, but generally it is not able to drive those values to 0 in most of the cases. But lasso has this ability to not just reduce the values but also drive most of the parameter values to 0. So if the coefficient or the parameter for a certain class becomes 0 in case of lasso regularizer, in that case that feature is not required. So we can simply remove those features for which the coefficient values have become 0. So that is what feature selection is, that we keep only some of the features and discard some of them. So for which the coefficient values become 0, we can discard them, which is possible in lasso, but in case of ridge this doesn't happen. This is not likely that you will get the coefficient values as 0. So that's why option B, lasso, is the correct answer. It is appropriate for feature selection. Now question 11. So there are two classes, plus and minus. I hope all of you can see these are the plus points and these are the minus points, representing two different classes, plus and minus, and these are the different points plotted on this 2D plot. While performing LDA on it, which line is the most appropriate for projecting data points? So LDA can also be used to do feature reduction, that is projecting the data points on some derived directions in order to reduce the dimension of the data points, or for feature reduction. Different straight lines are drawn here. This is one, this is one, this is one, this is one, of different colors. So you have to find out while performing LDA on it, which line is the most appropriate for projecting the data points. So red, orange, blue, green, which line is the most appropriate? Sweta Lakshmi says option C, Devasi says option C, Lakshmikant says option B, Anagha says orange, which is option B. Tejasvi says C, Mani says B, Sweta says B, Akash Manha says C, Sangeeta Vinayak says B, Prakash says C, Vrishali says B, Anantapalli says B, Sanvi says B. The correct answer here is option C, blue. So from the figure you can see that these are the two different classes, two different Gaussian distributions representing two different classes. The first one is the for the plus class and second one is for the minus class, and let's say this is the midpoint for the first class and this is the midpoint for the second class. So LDA projects the points in such a way or creates derived directions or features in such a way that the derived the projecting straight line will be parallel to m2 minus m1. So m2 minus m1 vector is this one. This is the m2 minus m1 vector or straight line, and the projecting line will be parallel to this m2 minus m1 line, and we can see that this blue straight line is parallel to the line segment joining the two centroids. So it will find out that by projecting the data points on this blue straight line, it will be able to reduce the dimensions. And also, as in LDA, the objective is to increase or maximize the inter-class variance. So by projecting the data points on this blue straight line, it will be able to maximize the inter-class variance. So blue is the correct answer here.
Does LDA depend on the number of examples in each class?
Yeah, LDA certainly depends on that prior values pi that tells you what fraction of points belong to a certain class, pi 1, pi 2, pi 3 for different classes. So it also depends on those.
Okay, if it is asked that separating decision boundary, then it may be
decision boundary, it would be orange.
Orange, okay.
Yeah, but LDA can be viewed in two different ways. That has been taught in the class also, that simply for classification using the probability values, and the another way of doing it is to see it as a projection of the data points. So it will project the data points onto this blue straight line so that the interclass variance is maximized, and it is also parallel to the line segment joining the two centroids.
But when it is projecting, that pi will not make a difference, no? I mean, irrespective of how many points are there, that it will not make a difference.
Pi, it is parallel to the straight line joining the two centroids, but whether pi would be affecting it, I am not completely sure. I don't have the complete expression.
Can you please write the equation for using pi for LDA?
There's a big equation, but the actual way of doing it is that we want to find out what is the probability that a given point belongs to class K is equal to, we can simply simply apply the Bayes theorem here, divided by summation of this over K. So this P of K is basically probability for the class K, which is the prior value for K. So if the prior value is high, then it gives a higher probability of belonging to the class K for the point X.
From this equation, can we understand that projection also?
No, from this you cannot understand the projection part. Projection part is, this is one way of viewing LDA, that is another way of viewing LDA, that projecting data points and feature reduction, that is another way of saying LDA. But here the question is that the straight line but the data points to be projected is parallel to the line segment joining the two centroids, which does not depend on the priors in this case, or even these probability values.
So LDA uses Bayes theorem only.
Yeah, LDA uses Bayes theorem. So that is one way of seeing LDA. Another way is the projection of data points. That is different. But
But is there
using
any
this,
other method called Bayes theorem? Bayes theorem means of classification or something where the same equation is used, or
yeah,
whenever
yeah.
Bayes theorem is used, it's called LDA.
No, naive Bayes is also one of them. In LDA, it is assumed that the classes are Gaussian, so it becomes LDA. And naive Bayes is another theorem which does not assume that the data points are Gaussian. So that is different, which will be taught in the class later on. That also uses Bayes theorem, naive Bayes, and LDA also uses
But
Bayes
which
theorem.
is better, or which is better out of
There
this?
is no better or worse, because different applications require different kind of algorithms.
Can you please tell one example just to make us understand that point?
No, there is no better algorithm as such. Naive Bayes is used for text classification. In other examples, LDA you would use where you know that the decision boundary is simpler or only linear. You
No,
don't need
actually,
complex.
we will be using LDA only when we know that the distribution is Gaussian, like that.
Yeah, it is assumed that the distribution is Gaussian in LDA. So if you are almost sure the data points for each class is a separate Gaussian, almost like a Gaussian, in that case LDA can be used. And also you should make sure that the straight line is not much complex, it is only a linear decision boundary.
One more doubt actually, how do you explain that posterior and class condition and all with respect to this equation and figure?
Which one?
This class condition probability, posterior probability, all that
Yeah,
on the
this,
figure also, can you please
yeah,
show
now
how
from figure you
what
cannot
it
see the,
means?
from this equation you can say this is the posterior probability of k given x. This is the pk, which is pi k also, it is the prior probability for a class, and this is the likelihood, class likelihood it is also called, probability of x given k. So for a given class, what is the probability of k? This is Gaussian distribution or normal distribution. This px given k is assumed to be a Gaussian distribution in LDA.
P of k is the value.
P of k is the prior value, that is a fraction of points belonging to class k.
And a denominator is also a value like that.
Yeah,
Denominator,
denominator you can
or it is
it is constant for every for the whole set of points, because it is summing over all the k
but
values.
actually, or is it like a Gaussian distribution in the denominator also?
Denominator is not really required. You can simply ignore this denominator and put this proportional value to it. You just need to compute the
And what is the
numerator.
class? What do you mean by class condition? Class condition probability.
Class conditional, I'm not sure which terminology is used in the lectures exactly. Class, because I don't know whether probability x given k is referred to as class conditional in the video lectures, but it is the likelihood probability basically.
Okay.
Okay, so these were the practice problems that I wanted to discuss in this live session. And now if you have any other questions or doubts, you can ask me.
What is this Fisher discriminant? That one part.
Yeah, there is a Fisher criteria, that is this j theta is the objective function that we want to maximize. Sorry, not here. So we want to maximize this j theta, which is given by yes.
This is for LDA, or for which one is it used?
This is for LDA. So this numerator m1 minus m2 square, m1 is the mean or the centroid for the first class, m2 is the mean or the centroid for the second class. So m1 minus m2 whole square gives you the interclass variance, variance between the classes, two different classes, and this and the numerator gives you the intra-class variances, delta 1 square plus delta 2 square. So we want to maximize this so that the intra-class variance is maximized, inter-class variance is minimized. That is one of the objective functions that is used in LDA.
What we finally it is
I cannot hear you properly. There are
J of
some.
theta. No, what is the J of theta?
J of theta. Which one? J of theta.
No,
This
it
yeah.
will tell us which class that
Yeah, J of theta is the objective function that we want to maximize with respect to theta, or here omega was there, I think. I'm not sure. So this theta is the parameter of the method. We want to maximize with respect to theta.
Sir, can we get the notes of this session?
Yeah, I will share these. I mean, these
this
notes
is
will be
only for
uploaded
LDA.
later on.
This is only for LDA, is it so?
Yeah, it is for LDA. Fisher criteria. This is objective function for LDA. So one way of
No,
viewing
but
it.
sometime back you said it was Bayes theorem. So this one
No,
I did
I
not
mean,
understand how
so
many
there
things
are
are
two.
coming.
I already said there are two ways of viewing LDA. One is using that Bayes theorem, probability value calculation, and another is for projecting the data points. This is for the projecting the data points. The data points will be projected as is theta transpose x. So we want to find out these theta values from this Fisher criteria. So that is one one approach of LDA. This is another approach of LDA. Both the approaches give you the same discriminant, the decision boundary finally, but two approaches of doing it.
Oh, okay. Okay, finally we'll get the same result whether we go like this or that.
Yeah.
Okay. Have a data for one class with some n number.
I cannot hear you.
And
There are a lot of noises. I cannot hear you properly.
and am I audible? Am I audible now?
Yes.
So actually, suppose for the same class, you have one set of examples and another set of examples, and you are trying to make a boundary. Will the boundary be different depending on the examples also for all these classifiers, logistic and LDA and all that? Will it vary with because different people may be collecting different samples. So will the decision boundary be different for different people like that?
Are you asking for different algorithms? Whether it will be different?
All the algorithms, just to understand for all the three algorithms, whether it is
If the data points are different, then the decision boundary might also be different.
For the same class.
Yeah, for the same. For the same algorithm, if you're asking, for the same algorithm.
It is suppose we are trying to. It is the same problem that three different people are doing, and one person is using one data set, but another person is using another subset of two people are using from the same data set, but they are using two different subsets of examples. Will they both finally arrive at the same
final
decision
output
boundary?
might be different. Yeah, it is highly likely
So
that the
which one
final
will
output will not be exactly the same.
Which one will be giving the most accurate output?
Yeah, that completely depends on the data points. If you take the whole data set, that would be much better. If you are not able to use the whole data set, then obviously you are using lesser amount of data, so your model might not be perfect.
Is there any thumb rule like you should use logistic regression for this case, LDA for this case, like that? Which one do we select to use when, like that?
There is exactly no such thumb rule as such. You might apply multiple different algorithms and compare their accuracies. For logistic and LDA,
Okay.
there is no thumb rule that in this problem logistic is better in some other problem. In case of LDA, that we assume that the Gaussian distributions are used. If you know that the data points are distributed in Gaussian distribution, then you can apply. Otherwise, if you are not sure whether the data points are Gaussian, then it might not give you a good result.
In one of the questions, you mentioned a Bernoulli distribution. No, where does that
Yeah,
come actually?
that is different. So Gaussian, this is the for x given k, it is LDA assumes that this distribution is Gaussian distribution, but there it was it would be better if I write it as y only, y, and so y given x, this probability, this random variable is Bernoulli. It can take only two
Okay,
values, y
okay.
equals 0, y equals 1, two different random variables. So you should not mix up those two.
That is for classification only. It will come like that. No, for classification
Yes,
only it
yes.
will come. For regression, we cannot take. Okay.
Yeah.
Hello, sir.
Yes.
I'm audible.
Yes.
Sir, can you explain the one of the example to calculate the likelihood for the logistic regressions? Any of the example?
I don't have any examples as such. Is it there in the assignment? Is there any question in the assignment in week 3?
I don't know exactly.
I don't have any such examples, but calculating likelihood, you can search in the internet. There are many different resources to show you different steps of the calculation, but I don't have any.
Any fixed equations for that to calculate the likelihood, or dependent values we need to calculate that likelihood?
So the log likelihood that is used in logistic regression is given by something like this. Notations might be different in the class. I don't exactly remember what notations are used. So this is the likelihood for n different data points. You have to calculate this to get the likelihood. Yi log h.
Likelihood is a distribution.
Yes.
Likelihood is a value or a distribution.
Likelihood is just a value. Log likelihood is just a value. Likelihood itself is a probability. Yes.
Is it a distribution or a single value?
It is a single value over the set of points. I equals 1 to n.
You know, when you wrote Bayes theorem, you said that likelihood was a distribution.
Now, likelihood is a distribution, but if you want to find out the likelihood value for a given data set, it will come out as a single value. Every probability distribution would have a specific value if you give the input to the probability distribution. So, if you compute the likelihood value for a complete data set, it will give you a single value, but overall likelihood is a probability distribution, obviously, and you can compute the values for that on a single specific data points.
Okay. Okay.
Sir, do you recommend any sources to learn all these concepts of LD and regression? Any standard books or resource?
Standard book, I mean the textbooks recommended for this courses for this course are already written in the course homepage. There are two books recommended. One is
only the transcript. No, in the course homepage, only the transcript was found. Is it written somewhere else actually?
no, don't log in into the portal. Before logging in, you have one course homepage, but you have the description of the course, professors names, and the syllabus, and there two books are written there. One is Elements of Statistical Learning, I think, and another one is Another one is pattern recognition. I think, let me check. uh,
Previous year's assignment questions, is it also available?
Not that. Let me. Yeah. In the course web page, yeah, two books: the elements of statistical learning, and pattern recognition and machine learning. Go to the online
No.
courses.nptel.ac, and for this course, you will get that.
How about assignment questions of previous years? Is it available anywhere?
Assignment courses, no, I'm not aware. For previous years, I don't know.
Because some any more practice questions or something, because we are getting only some 10 problems, no? To know more, or do whatever you're sharing, is it from some common database or something?
Mm, uh, no, some of the questions are from different sources. Different courses are from different sources, but NPTEL does not provide any such
Okay.
questions from previous offerings. Okay, if there are no other questions, we can end this live session. Thank you everyone for joining.
Thank you.
Okay, sir. Thank you, sir.
Hello,
Yes.
sir. Sir, I have posted one question in the chat. Please answer this.
Okay, Devashish, when will LDA and logistic regression produce different decision boundaries? It is likely that they will produce different decision boundaries in almost all the cases, because the loss function that these two are using are completely different. So different decision boundaries would be created. So it would most likely that in most of the cases decision boundaries would be different. There is no specific case that LDA will produce one specific decision boundary, or the logistic regression will produce some specific decision boundary, but the loss functions are completely different. So it is most likely that in all the cases these two will produce different decision boundaries. Okay, thank you everyone for joining.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Yeah, thank you everyone.